Morning, students. In the last lectures we have discussed what is lability and inertness. Today we are going a step further and we are going to discuss what are the factors which affect the lability of the complex. Although there are several factors depending on different type of metal ions, but we can figure out two general factors on which the lability of the complex depends. One is the charge on the central metal ion and another is the radii of the central metal ion. The charge on the central metal ion decides the lability that in case of highly charged species, they form complexes that react very slowly. For example, we can take the C in this case of aluminium, silicon, phosphorus and sulfur. The sulfur is the highest charge +6, but it reacts the slowest one. The lability of this reaction is very slow. The lability means we can, in case like the substitution for fluoride happens for aqueous solution, that water as a ligand or other ligands are being substituted in case of fluoride. The other factor is the radii of the central metal ion. The central atom which have small ionic radii react more slowly than those having larger central ions. Okay, now suppose in this case we can discuss this example where magnesium, calcium and strontium we have taken. Now the radii of strontium is the biggest, that is 1.13 angstrom, and charge on the complexes are similar, but we can see the lability is differences there. The strontium is more labile compared to magnesium because it has higher charge. So we can just further discuss about the charge to radius ratio also, but this just is applicable only for octahedral complexes. Square planar complexes doesn't follow that. So we are sticking to only two major factors, that is charge and radii. Now we are going to discuss one more parameter, that means the stability of the thermodynamic stability of the complexes. We have discussed this is little brief in our previous video. Now according to thermodynamic stability, we can discuss the stepwise formation of the complex. What Jerome was a scientist who discussed this in quite detail, the stepwise stability of the complexes. According to him, what he said that the complexes are formed by the reaction of metal and the ligand in a stepwise formation. Now the stepwise formation can be chosen by the complex. What I want to say, let's see the example and then we are going to discuss it in detail. Suppose it proceeds stepwise. Stepwise means the metal combines with one ligand and forms a Ml type of complex. So the stability constant is given by K1. K1 is the first stability constant at equilibrium. Since we are talking about thermodynamic stability, obviously we are going to talk everything at equilibrium. We have discussed till now all about kinetic stability. Now we are talking about thermodynamic stability. Now how the K1 will be given by the product upon the reactant, right? Similarly, the K2 can be given as the product divided by the product of the reactant. And similarly for K1, that is MLN, when MLN formation is MLN minus 1 plus ligand. So what it will be, MLN divided by MLN minus 1 into L. Now these are called as stepwise stability constant. Now there is one more way in which the complex can be formed. What is that way? The formation of the complex can also take place in the following way. The metal and the ligand combines in the first step and forms Ml, or in the second step we can say that all the ligands together combine with metal to form Ml2. Or in another way, the metal combines with all the extra ligands, NL ligands, and forms MLN directly. Now what will be the stability constant in this case? Obviously beta 1 will stay same as your K1, but further stepwise stability constants differ. The ML2, then ML and L raised to power 2. Remember how we used to write the stability constant in the reaction kinetics in 12th? The same way. Okay. Now these are called overall stability constants. Overall stability constant. Higher the value of the stability constant for a complex ion, obviously greater will be its stability. So we can figure out then whenever the value is higher, any value, whether it is you are talking about beta or you are talking about K in terms of K, higher the value of the stability constant for a complex ion, greater will be its stability at equilibrium. Obviously we are talking because this is thermodynamic stability. Okay, got it? Now let's derive a relation between beta and K. This comes sometimes in as a 2-marker question. The relation between beta n and Kn. We are going to start with supposing that there is a beta 3, that it's a third step. There is a beta 3 where ml3 and m and l, which is given by the product of ml3 divided by m and l raised to power 3. Now in case on multiplying both, we will multiply both the numerator and denominator with m and ml2. Okay, and rearranging we get what? ml3, ml and ml2 divided by ml cube. Again we are multiplying with ml and ml2. Now let's rearrange and reshuffle them. We can write them like this: ml divided by m into l. We have taken this here. Okay, taken this here and one of the ligand here. Then again we have written this ml2 here, this metal ligand here, and one more ligand comes here, right? Then again this ml3 comes here and the same thing follows. Now we can see that we have brought it into a format that we can directly write this is equivalent to K1, this is equivalent to K2, and this is equivalent to K3. So now we have derived a relation, that is beta 3 is given by the product of K1 into K2 into K3. Or beta n we can write as a general formula summation of Kn, right? Or if in terms of we want to express in terms of log, then obviously it is log to the base 10 K1 plus log to the base 10 K2 plus log to the base 10 Kn. This is the final relation, either this one or this one. You can leave it up to any point, or this one, when you are asked to derive a relation between beta n, stepwise stability constant, and overall stability constant. They will sometime won't ask with beta n Kn, where they will ask stepwise stability constant, that is Kn, and overall stability constant. So you can derive the relation. Okay. Now, since we have discussed these things, we are going to start with a new topic, which is called reaction mechanism. Inorganic reaction mechanism. We are going to discuss it in our next video. Thank you.